It started somewhere in Central Asia. Elusive, it glimmers from deep in ancient and medieval texts, a reference here, a passing mention there about a mysterious phenomenon to the east. No one knew how or exactly when, but from Central Asia it began to spread outward during the early Middle Ages. Merchants, travelers, and their caravans carried it along the Silk Road to Africa, Europe, and China. None of them knew that what they carried would set in motion a train of events that would someday cost millions of lives and change the face of civilization. I'm talking, of course, about crucible steel technology. From at least the first century AD, Central Asia, what are now Uzbekistan and Turkmenistan, was renowned as the place that produced better swords, spears, and armor than nearly anywhere else. By the 800s AD, Central Asian steels were famous far and wide for yielding blades that were without equal for toughness, flexibility, and holding a good sharp edge. By a few hundred years later, they had acquired the misnomer Damascus steel and were generally considered a late medieval form of kryptonite. Travelers and crusaders would come back from the Holy Land with tales of the astonishing swords, spears, and armor obtainable only in the East and at vast prices. Let's look at what happened and how. The best place to start is with iron, which had already been in use in Central Asia for several hundred years by the time it became a steel-making center. Iron is a great material, but despite its ironclad reputation, it actually has quite a few disadvantages in practice. Iron can be made pure and it will be quite tough and won't rust, but it's very soft. In fact, it can be softer than some types of bronze. Its drawbacks were documented by the Roman historian Tacitus, who recorded that otherwise formidable Germanic warriors periodically had to retire from the heat of battle and jump up and down on the flats of their swords to straighten out the curvature that their soft iron had developed on contact with Roman shields. That problem can be fixed by introducing some carbon, creating an iron carbon alloy that is nice and hard thanks to the formation of super hard iron carbide crystals. Unfortunately, for chemical reasons, iron will naturally tend to acquire too much carbon, leading to a result that, though hard, is extremely brittle. So instead of bending on contact, a sword or spear point made from this kind of iron would tend to shatter, which is also not conducive to success in battle. The trick for Damascus or most other types of steel is to split the difference. If you can control the carbon content of the iron down to between about 0.5% and 2% carbon, you can create a steel, an alloy that consists of a mix of hard but brittle iron carbides embedded in a matrix of soft but flexible pure iron, giving you the best of both worlds. That may sound simple, but with ancient and medieval technology, it was very hard to do and even harder to do well. And that was where Central Asia, starting during the time of the Roman Empire, was at the cutting edge of technology. Their first step in steelmaking was to make iron, pretty much the same way everybody else did at the time, by mining iron ores, packing them into a small type of charcoal furnace called a bloomery, and lighting it up. The temperature never got hot enough to actually melt the iron, but it was hot enough to start the carbon from the charcoal diffusing through the iron ore, stripping oxygen out of it and leaving a lump of pure iron, along with a glassy mix of silicate contaminants called a slag. Now, in most parts of the medieval world, this mix of iron and slag would have been taken straight from the furnace to the forge to be worked into plain iron, but in Central Asia, some of it was instead hauled off to be made into steel. This involved packing it into small crucibles specially manufactured to resist heat and corrosion, spiking the mix with some manganese ore, covering it with dry wood or leaves and a lid, and heating the crucibles about a dozen at a time to nearly 1500 degrees C for several hours before allowing them to cool slowly down. During that time, the carbon from the wood or the leaves slowly diffused through the dense molten iron, but the liquid slag layer floating on top of the iron restricted the amount of carbon that could get in. The manganese diffused in too, forming ultra-hard manganese carbides and a manganese iron alloy. The presence of the manganese also caused the iron carbide grains to start lining up instead of facing in random directions as they normally would. Very often, other carbide-forming impurity elements like chromium and vanadium were present in the ore as well and did likewise. So when the crucibles were finally pulled out of the furnace and broken up, the contents were small egg-shaped ingots of what would now be called a high-carbon manganese steel. When forged at relatively low temperature, the alternating lines of carbides and iron manganese alloy would form a beautiful pattern that would become visible when the surface was cleaned and etched. This patterned steel, stronger, harder, and sharper than anything else then known across the world, was called pulad or bulat. In the Persian Avesta from the early centuries AD, Pulad steel was the sacred metal of heroes, gods, and kings, and in oral traditions, its magical powers included warding off evil spirits. We're not too sure about the evil spirits, but Pulad steel could certainly ward off enemies with great effectiveness. It was basically a modern superalloy steel in a medieval setting, impressive at any time, but unbeatable then. There's an apocryphal story that the Crusader King Richard I of England tried to impress the Muslim conqueror Saladin by splitting a blacksmith's anvil in half with one mighty blow of his sword. Saladin replied by tossing a silk scarf in the air and holding his Damascus steel sword underneath it. The scarf drifted to the ground in 2 pieces. That story is made up, as far as we know, but from a metallurgical standpoint, its least realistic part is Richard's sword being able to split the anvil, not Saladin's being able to split the scarf. That was actually one of the 4 tests that a true Pulad steel blade was supposed to pass. The Persian scholar al-Biruni in the early 11th century listed it with 3 others. The sword should give a good, clear ringing sound when struck. It should cut through an iron bar without the blade being notched, and it should bend 90 degrees and spring back undeformed. The earliest known Pulad steel blades date back to at least the 1st century AD in Central Asia, and over the ensuing centuries, production grew. By the 9th to 10th centuries, steelmaking was a large-scale regional industry. Archaeological remains that are still being excavated include more than 100,000 crucibles at a massive foundry in Aksaket in what's now Uzbekistan. Far more steel was produced there than could have been locally used, and much of it appears to have been intended for a long-distance export trade. Sent east to China, it was called pintie, and Chinese writers described it as a patterned steel so hard and sharp that it would cut stone and metal alike with ease, and that cost more than its weight in silver. Pulad steels were popular in the armies that spread Islam around the Eastern Mediterranean, and trade took them further still. Leaders of the Sassanid Persians, the White Huns, the Kushites, and even the Vikings armed themselves with Pulad steels from Central Asia. By the early 1200s, Pulad steel had acquired the name Damascus steel, at least in the Islamic world. The same name was also applied to a crucible steel called woots, which was made in South India and Sri Lanka by a different process that yielded some similar properties. In both cases, the Damascus tag probably reflected where it was traded through or manufactured. Another possibility is that the category was named after a particular swordsmith called al-Damaski. That would not have been uncommon, as particular workshops and artisans working in Pulad steel developed and maintained brand identities for their products. At least around the Islamic world, having been made by a particular swordsmith or workshop was a guarantee of quality for the best swords. In the rest of the world, however, consumers mostly relied on the blade having a Damascene pattern, which was considered an indicator of very high quality. If the blade had been made from a crucible steel, this indicator was probably accurate. However, Damascene-like patterns could also be produced by pattern welding ordinary iron and carbon steel. Such lower caliber imitations were frequently passed off as genuine Damascus crucible steel products, thereby demonstrating that the advertising industry has not changed in the last millennium. In roughly the 1220s AD, the Central Asian steelmaking heartland received an unwelcome visitor in the form of Genghis Khan. Historical accounts give the casualties of his invasion at well over 500,000 in the city of Merv alone. Among the things that never recovered from the Mongol conquest was the manufacture of Poulad steel. Large-scale production ceased, and what little could still be exported stopped reaching Europe. But Poulad steel continued to be made, mostly in small individual workshops, and a little of it was still traded to neighboring countries over the ensuing centuries. Demand, however, didn't go away, and the next few hundred years saw many attempts to bolster supplies of Poulad steel for various nations. The Russian Tsar Alexei, father of Peter the Great, sponsored an industrial espionage mission abroad to learn how Poulad steel was made, and for good measure, he commanded officials in the Central Asian realms of the Russian Empire to round up and deliver to Moscow any blacksmith who knew the art. Further west, French and British scientists of the late 17th century busied themselves with unsuccessful attempts to replicate it. All these efforts fizzled in the 1700s. Under Peter the Great's westernizing influence, Europe became the preferred source for Russian technological as well as cultural imports, and Central Asian steels were frowned upon. French and British experiments, having ended in failure and frustration, languished for a time. Around 1800, shortly after the pattern sword became fashionable among army officers, European interest in Damascus steel picked back up. The turning point came in 1818 when a baffled scientist of the British Royal Society approached Michael Faraday with a Poulad ingot and asked if he could figure out how it was made. Faraday was a blacksmith's son and bookbinder's apprentice who had worked his way up to become the foremost figure of British science at the time. Stimulated by the unique properties of the Poulad steel ingot, he embarked on a campaign of experiments in iron metallurgy, which saw him develop new alloys of iron with every metal from silicon to platinum, and discover some of the theretofore missing fundamentals of the metallurgical process. But Faraday did not manage to uncover the secret of Damascus steel. That honor would go to Pavel Anosov, a Russian metallurgist assigned to a government-run arms factory in Zlatust, south of the Ural Mountains. In 1819, he was supposed to oversee production of imitation Damascus steel sabers for the adornment of wealthy officers. Not satisfied with producing such imitations, with a few real Poulad samples in hand, and possibly bored out of his mind in suburban Zlatust in the evenings, Anosov began a quest to find out how to make genuine Poulad steel. Legend later had it that he traveled east, infiltrated a workshop, and extracted the process at knife point from an unwilling master blacksmith. In reality, his success was the result of more than a decade of careful experimentation and diligent microscopy. By the mid-1830s, Anosov's supposedly decorative division was turning out genuine Damascus blades made from freshly manufactured Poulad steel with a scale and quality that had not been seen for 600 years. In 1842, in what was probably a token of appreciation and not at all a major metallurgical neener, Anosov sent Faraday an inscribed example of his output. But in the long run, Faraday's failure would have more impact on the world than Anosov's success. Perhaps because he had advocated for better treatment of the serf workforce employed at the arms factory, Anosov had incurred administrative wrath and was reassigned to southwestern Siberia. He died there in 1851 before he could finish writing up and publishing his work. Erasing what they saw as the double plus ungood innovations associated with that particular unperson, the Russian officials discontinued the production of Poulad and reverted to importing steel from Britain and Austria. In the meantime, Faraday and other European scientists were making rapid strides in the production of new alloy steels. In the ensuing decades, their experiments would lead to a bewildering array of steels with properties comparable to those of Damascus steel, but which for the first time could be cast and mass-produced into large objects like artillery and armor plating. Toward the end of the 19th century, these new gun and armor steels would kick off an arms race, and in the resulting World War, they would be put to devastating use. Archaeologists are still uncovering much of the starting point of this long and complex chain of events, but even the fragments make clear that the steel technology of Central Asia was unsurpassed in medieval times.